the Moon's strange magnetic scars. For most of the space age, the Moon was thought to be magnetically quiet. Any internal field it once had was believed to have faded billions of years ago, leaving behind only faint traces preserved in ancient rocks. Apollo astronauts did bring home fragments that carried remnant magnetism, but these were interpreted as records of a primordial dynamo that no longer operated. Without a molten, convecting core to generate currents, scientists assumed the Moon had no present sources for strong magnetism. The picture felt consistent, a geologically frozen body, chemically arid and magnetically inert. But as spacecraft carried more precise magnetometers, the consistency began to unravel. Certain orbits revealed unexplained distortions. Some probes crossed regions where particle instruments recorded plasma disturbances over specific craters. For years, each anomaly was dismissed as minor or localized interference. Then, with the return of high-resolution data from orbit and new analyses of samples from missions like Chang'e 5 and Chang'e 6, a much stranger picture came into focus. Instead of being uniformly silent, the Moon's crust was revealed to contain scattered hotspots where magnetic intensity spiked unexpectedly. These were not traces of a global field, but concentrated zones of localized magnetization, sometimes strong enough for local crustal fields to deflect streams of solar wind particles and create small-scale protective effects. These magnetic scars appear across various regions of the lunar surface, but are especially concentrated in areas of geological and resource interest, including the polar environments believed to harbor ice deposits in permanent shadow. The overlap was more than coincidental in appearance. For many researchers, it raised a key question. Could these crustal anomalies be quietly shaping how volatiles survive on the Moon's surface? The return samples have underscored the reality of these magnetic concentrations. Laboratory measurements on lunar soils from Chang'e 6 found high abundances of ferromagnetic minerals, metallic iron and Fe, alloys, that can carry strong remnant magnetization. These analyses reported saturation magnetization values higher than Apollo and Luna samples, confirming that significant populations of magnetic grains still exist in the regolith. The fact that fresh material from the South Pole, Aitken Basin, shows such properties, even in an environment where the modern dynamo field has long since collapsed, demonstrates just how substantial the magnetic memory of the crust remains. In some places, these signals are strong enough to disrupt orbital measurements, forcing a reassessment of decades of data once thought straightforward. Such magnetic anomalies matter because they alter the interaction between the solar wind and the lunar surface. The solar wind, composed of charged particles, typically bombards the regolith directly, implanting hydrogen, sputtering exposed volatiles into space, and slowly eroding surface stability. But where localized magnetism diverts those ions, the environment changes. Even weak patches of shielding can reduce the flux of bombardment, lessening loss rates and subtly affecting how volatiles migrate or remain in place. On long timescales, these protective effects could mean the difference between an ice deposit persisting for eons or diminishing away. In this view, lunar water is not governed by cold traps and shadows alone. Instead, invisible magnetic overlays may contribute a second layer of defense shaping, where usable pockets of moisture survive. The South Pole, Aitken Basin, offers one of the clearest case studies. It is the largest and deepest impact basin on the Moon, stretching more than 2,500 kilometers across. Along its northern rim, orbital magnetometer data reveal pronounced crustal anomalies, while its central interior shows much weaker magnetization. The difference is thought to arise from the distribution of impact ejecta and the composition of material reworked during immense collisions. The Chang'e 6 soils came from within this basin, and their magnetic measurements provide ground truth to support orbital charts. Yet the paradox remains. The soils carry a high remanence capacity, but their landing region today shows relatively weak field strength. This suggests that repeated reheating by later events may have demagnetized areas even though the constituent minerals remain capable of carrying strong magnetism. The origins of the anomalies are still debated. One explanation ties them to an ancient lunar dynamo, a convecting, molten core that may have persisted much longer than once assumed. Some Apollo samples record strong magnetization dating back 4 billion years, while others suggest younger episodes around 2 billion years ago. Another hypothesis adds exogenous contributions from iron-rich meteorites. Impact-generated melts mixed with fragments of meteoritic metals could have carried and preserved magnetism upon cooling. A third possibility, modeled in a 2025 study from MIT, proposes that a combination of a weak ancient magnetic field and the plasma cloud from a huge asteroid impact could have temporarily amplified magnetism on the Moon's far side. In their simulations, the flow of ionized material concentrated field lines in localized regions, strong enough that rocks cooling during that interval would lock in unusually high remnant magnetization. Each scenario is testable, but none yet definitive. The anomalies may reflect overlapping influences of internal and external processes operating across very different eras. This uncertainty makes it tricky to pin down the precise link to volatiles. While it is tempting to claim magnetic anomalies directly preserve ice, the connection is more nuanced. Local shielding can lower sputtering rates, but it cannot stop thermal escape in regions subjected to direct sunlight. Conversely, cold traps without shielding can still preserve ice purely through extreme low temperatures. The most realistic view is that magnetism is a partial factor. In some places, where shadow and magnetism coincide, volatile survival may be enhanced relative to equivalent craters lacking residual fields. This could help explain aspects of the irregular distribution seen in orbital and in situ measurements. Still, researchers emphasize the point remains an open area of investigation rather than a settled cause and effect. What emerges clearly, though, is that the Moon's environment cannot be treated as uniform. Every anomaly changes plasma flows, particle implantation, and perhaps subsurface heat transport. Some sites create conditions friendlier to volatile retention, others do the opposite. That variability complicates exploration planning. If future landers or rovers arrive at unshielded sites, they may struggle with resources sublimating faster than expected. Just a short distance away, deposits under magnetic protection could prove far more accessible and durable. For mission design and long-term settlement, knowing which invisible scars provide these advantages could make the difference between success and costly disappointment. The revision to old models has also forced researchers to correct decades of interpretations. Earlier missions assumed the Moon could be analyzed as magnetically inert, and their instrument calibrations reflected that assumption. Now each pass over a known anomaly requires adjustments, mapping hydrogen signatures, modeling thermal gradients, or predicting dust dynamics without accounting for crustal fields risks, mistaking magnetic influences for other phenomena. The recalibration effort is ongoing, but it underscores how blind spots in assumptions cascade through entire fields of data. Magnetism may even tie into thermal properties of the crust. Variations in conductivity around magnetic patches suggest that aligned minerals could affect how heat flows from deeper rock to the surface. Since volatile stability depends on both surface temperature swings and subsurface thermal gradients, this further complicates predictions. A magnetic site might stabilize volatiles through solar wind deflection, while at the same time destabilizing them by channeling heat differently. Understanding these competing influences will require integrated surveys that look at magnetism, temperature, and volatile signals together rather than as isolated layers. Looking ahead, future lunar missions are beginning to account for these discoveries. Instead of drilling in shadow alone, they will combine shadow maps with magnetic field charts to prioritize promising sites. Instruments capable of measuring surface magnetism while simultaneously probing for hydrogen or ice deposits will test whether protected overlaps are more consistent reservoirs. Sample return efforts will refine how magnetic minerals record these conditions, building a deep-time history of both the lunar interior and its surface environment. For human presence, this knowledge could reduce the need for redundant extraction systems if natural shielding already lowers the rate of volatile loss. The lingering mystery, however, is not just practical but historical. What do the scars say about the moon's past? Were they frozen snapshots of a gradually dying dynamo, or were they formed in brilliant surges when impacts, plasma, and weak fields interacted at dramatic scales? Answering that will link lunar magnetism to broader planetary evolution, offering clues about how bodies lose and retain magnetic engines across solar system history. What is clear is that the moon carries a legacy much messier than the tidy picture once drawn in textbooks. Its scars are neither random quirks nor trivial artifacts. They shape plasma environments, they influence volatile persistence, and they complicate our maps of where humans can find resources to survive. Whether fragile guardians of ice or relics of a vanished dynamo, they represent an active arena of research and a reminder that even in silence, the moon records forces still capable of shaping its surface conditions today. And yet, invisible scars are not the only proof that the moon's story is unfinished. Other signals now indicate it may be more restless than its still landscapes suggest, with unexpected activity continuing to reshape the places we thought would never change. When the moon refuses to sit still, the picture of a geologically frozen moon has lost much of its certainty. For decades it was assumed that nothing beneath the surface had moved in billions of years. Volcanic fires were long gone, tectonic stresses had relaxed, and the quakes that Apollo seismometers once registered were thought to be nothing more than minor thermal contractions. Yet recent geomorphic and remote sensing studies have overturned this view. In 2025, researchers analyzing lunar reconnaissance orbiter data identified 266 small ridges on the far side of the moon. Their crisp edges and lack of impact weathering mark them as geologically young, formed within the last 200 million years. At roughly the same time, laboratory studies of samples brought back by the Chang'e 5 mission revealed volcanic glass beads dated to just tilde 123 plus or minus 15 million years ago. Together, these findings show that the moon has experienced both tectonic deformation and volcanic activity far more recently than previously believed. Instead of a silent husk, it has been active well into the last few hundred million years. The evidence also reframes Apollo's earlier seismic results. Moonquakes were once attributed entirely to surface cooling, a passive process requiring no ongoing internal heat. But the distribution of the recently discovered ridges, folds, and scarps that match the lineaments of faults suggests crustal motion is still capable of reshaping the terrain. The ridges form when the moon contracts as it continues to cool over time, forcing rock upward along thrust faults. Gravitational stresses from Earth's pull can amplify that effect, producing surface shifts even now. If faults are young, then motion along them today remains possible, which explains why seismometers consistently detected bursts of activity that never quite fit the tidy narrative of a moon gone still. For settlements planned near the poles, this unsettles old assumptions. A ridge that formed within the last 200 million years is practically modern in planetary terms. If such features are still developing, polar ice reserves may not be sealed in ancient stability. Instead, they sit in a landscape vulnerable to movement. Quakes can expose buried ice, making fresh samples accessible, but they can also destroy protective traps, releasing reserves into space. That dual reality is stark. Quakes can expose ice, good for sampling, or destroy traps, bad for long-term extraction. Chang'e samples strengthen the case further. The volcanic glass beads found in 2020 and published on in subsequent years are distinct from impact-generated melts. Their sulfur isotopes, textures, and rare earth enrichments point to magma sources heated by radioactive elements within the mantle. The fact that eruptions persisted until only about 120 million years ago means the lunar interior retained localized pockets of heat long after global volcanism ceased. This has implications for polar volatiles. If such heating continued in regions beneath the crust, it could have created conduits for gases to migrate upward, aiding in volatile transport to colder zones. That idea dovetails with seismic evidence. Tectonic adjustments may be redistributing hydrogen and water even now, feeding polar traps more recently than the standard models assume. The connection between activity and water supply is not just theoretical. If fractures and scarps continue to form under stress, they provide pathways for material exchange. Solar wind hydrogen implanted in surface grains might migrate through these cracks, settling into colder interiors where shadows protect it. Subsurface volatiles disturbed by quakes may redeposit elsewhere, patching one reserve while draining another. Far from static freezers, polar trenches could be dynamic systems fueled by ongoing geological adjustments. This pushes researchers to consider that the Moon's water cycle may still be evolving, shaped by the planet's contraction and magnetic scars as well as sunlight. For exploration, unpredictability is as much a challenge as it is an opportunity. Artemis planners depend on reliable storage of polar ice to justify infrastructure for bases and fuel depots. But if ridges and the stresses that form them continue to reshape the ground, resource maps will require continual updating. The need for permanent seismic networks has moved much higher on the agenda. Scientists emphasize that understanding ongoing activity demands more than temporary lander stations. Distributed and long-term sensors are needed if we are to distinguish between shallow quakes tied to daily thermal cycles and deeper tectonic releases tied to internal cooling. At present, such a global network does not exist, but it is increasingly discussed as critical for exploration safety. Moonquakes also complicate engineering. Unlike Earth, the Moon's atmosphere cannot absorb vibrations or dampen energy. Seismic waves propagate more cleanly, traveling long distances with little loss. A relatively small release of energy can translate into extensive shaking, dislodging dust and destabilizing slopes. Habitats built near crater rims would be particularly vulnerable. Engineers now factor seismic resilience into designs for lunar bases, envisioning anchored foundations and structures able to withstand dust avalanches triggered by ground movement. There are wider implications for lunar science as well. If geologically young structures exist, earlier maps that assumed static topography need reconsideration. Dating of impact craters, the standard method to determine surface ages, depends on assumptions about background deformation rates. Younger scarps mean parts of the surface have been refreshed far more recently than time counters suggest. This adjustment reshapes not just our understanding of the Moon, but also comparative models for Mercury and Mars, which show similar tectonic contraction features. These developments converge on one important conclusion: assumptions of permanence cannot be counted on. Just as patchy ice distributions defied neat expectations, seismic and volcanic findings show that even the landscape itself continues to evolve. For water, this may be a mixed story. Renewed fractures keep cycles active, allowing new stores to form. Yet reservoirs can also drain through the same pathways. Future missions must account for both outcomes in order to avoid planning around false certainties.